And then Adam will present a variety of problems in this area, and then we'll go around and solicit more problems. And then we have ideas for larger scale projects, a possible idea for a foundation field. So we're using a technically more elaborate setup this time with more microphones and now and so forth. So if we do at least have one remote participant, let us know if there's something wrong with the sound or otherwise so that we can correct it. So with that, why don't we go around the room? You think I should turn the camera maybe, or maybe that temporarily makes sense while we're doing introductions. And so let's see, am I sort of visible? So, okay, so I'll start. I'm Mike Douglas here at the CMSA. I'm a physicist who works on a wide variety of other problems. And why don't we start? Should we start in the back this time? Maybe start in the back.
Your name player from University of Hampshire, and I study applications of machine learning methods and string theory.
Okay, thanks. Did the people? Okay, Francois is coming on. Let's just wait a minute, and then in fact, I'm going to ask you to speak louder and introduce yourself again. So is everybody connected? I assume so, just because there's no, okay, speak a little louder. And
so I'm Georgi Kupaya. I'm from University of New Hampshire, and I'm studying applications of machine learning methods and string theory.
Okay.
Hi everyone, I'm Tancredi. Tan is fine. I'm from Queen Mary, and I also do applications of ML in string theory, and I'm trying to do something with GR.
Hi everyone, I'm Tomás Silva from University of Campinas, Brazil, and I do ML plus algebraic geometry.
Henry Kavingi, I'm at Pacific Northwest National Lab, and among other things, I'm looking at applications of ML and ML interpretability to advancing algebraic combinatorics and other algebraic fields.
Hi everyone, my name is Berkan Şimşek. I'm a postdoctoral researcher at Flatiron Institute and working on theoretical foundations for deep learning.
I'm Morgan, I'm faculty here, and I work on ML theory and graph theory from the randoms.
Hi, I go by Q. I'm from Hankook University of Foreign Studies in Korea, but I'm on sabbatical, so I'm visiting my advisor at UIUC, and Adam invited me to come, so I'm here. I do graph theory and combinatorics. I do have some background in computer science, so I'm more like, I'm in math, trying to learn all these new techniques, trying to apply to math. So we'll see how it goes.
Hey, I'm Thomas Harvey. I'm an IFI fellow at MIT, and I mostly work on applying machine learning methods to string applications in geometry.
I'm Oxford student, and yeah, I also work in physics string theory in Chile.
Hi, I'm Fabian. I'm from Northeastern University. I'm in the math and physics department there, and I mostly apply reinforcement learning to problems that string theory throws at you. So that those are algebraic geometry, number theory, and also some low dimension topology.
Hi, I'm Jim. I'm a professor at Northeastern and a physicist, and I love thinking about math and computer science also, sort of very broad research interests.
I'm Kyuhan Lee from the University of Connecticut. I'm interested in application of machine learning to mathematics.
Hi, I'm Adam Wagner. I'm doing combinatorics and graph theory, and I'm interested as well in all sorts of applications of machine learning to maths.
I'm Vasily. I'm a new postdoc at CMSA. I'm doing geometric representation theory and Trinity University.
Okay, thanks. So why don't we go through the screen here? Aurel?
Hi everyone. I'm a number theorist at the University of Toronto, and I'm here because I want to learn more about using machine learning, especially reinforcement learning in mathematics.
Francois?
Yeah, hi, I'm François Charton. I work in Meta. I'm in France right now, but I was in Boston a few weeks ago. I'm mostly an ML person, and I'm interested in doing ML for anything related to scientific discovery and mathematical discovery.
Thanks. Really?
Hi, I'm Gergely Bertsi from Aarhus University in Denmark. I am a mathematician here, an algebraic geometer, and I'm interested in all sort of applications of machine learning in mathematics.
Thanks. Okay, so that's everybody. So, Adam, would you like to present?
Yeah.
Turn this around and then skip forward to it.
Yeah.
You'll need.
Let's share my screen.
That's right. I think I have to. Allow this.
Okay, so I think the goal for here today is just to start by gathering a bunch of problems that we're interested in. I would just get it started. I will just show you three really simple, oops, that's not what I wanted to share, sorry. Okay, I will just get us started with presenting just three very simple problems, and then other people can also present. We just go back and forth until we find something that we're interested in. So the first one I wanted to present is just something very, very simple. You have the n by n chessboard. You want to pierce every square of the chessboard, which means if n is 4, you want to find a bunch of lines that hit every single square in some interior point. So we cannot have lines like that go through this. We really want to hit the squares in the interior. And the question is, at least how many lines do we need to really hit every single square of the chessboard? So nice math puzzle, but it turns out to be surprisingly difficult to solve. So can someone give me some easy upper bound, some easy construction that is with n lines, you can obviously do it. Just say n horizontal lines, take this one, and so on. You can definitely do that. Turns out you can do a little bit better. There's a paper here by serious mathematicians, and they found a construction with n-1. But that's actually the best known. So it would be cool to try to find better constructions than that. I'm optimistic that you can do n-2, n-3, and so on. I don't know how difficult it would be, but it feels like this is a problem that plausibly could be finished within this week. And whatever method we come up with could also be interesting. And it also would be nice to see how you can do better than n-1. So just very, very briefly.
In all cases, it's clear. I mean, for 1 square, obviously you can't do better. For 2 squares, you can't.
Yeah, for n up to some small values, it's definitely optimal. And because
do you expect it to grow with n? Or?
Yes, definitely. So lower bounds, easy lower bound is n/2, because every line intersects at most 2n squares. So you need at least n/2 lines. And they improved it with some heavy maths to 0.7n. But I'm pretty confident that the upper bound is not correct. You can definitely do better than n-1. Maybe you have to go high enough to n equals 10, 20, 30, who knows?
So the bounds on n for that n-1 example, I mean, just in the 2x2 case, it doesn't seem.
Yeah, so
you
need at least n at least. Who knows? So it works already for n equals 3, right? N equals 3, I think you can do it 2 already. Let's see. So I hit these ones with the first line, and I hit these ones with the second line. I think I can do that. If I just put my lines very carefully, this probably works, and this also works. So I think n equals 3 is already enough.
Okay. So just n equals 2.
Yeah. And probably for n equals 10, 20, 30, who knows, n minus 2 is also possible. It would be nice to find constructions like that. This is definitely not like a famous, important, deep mathematical problem, but it's something that could be done in a few days. So I just wanted to get us started with this one as an option. 2 other quick options for problems. Here's a nice question of Erdős, and might be intimidating to hear that it's a question of Erdős, but it's one of those questions of Erdős that kind of got lost. So it has 1 citation in total, and that's also not really related to the question itself. So it seems like nobody has really worked on this problem, and it would be nice to think about it. The question is, you start with n-dimensional hypercube, so all 0 sequences of length n, 2 sequences that are connected by an edge if they differ in exactly 1 coordinate. The question is, how many edges can you delete without increasing the diameter of this graph? Completely open, nobody that I know of has really thought much about the problem. There is a construction, there's a construction with this many edges, and I can explain it in more detail, but very roughly, you take 2 opposite corners, take a breadth first search tree towards each other, and in the middle, just join them with perfect matchings. That's a construction that Erdős came up with. Question is it optimal or not? I have no idea, but this could be a fun problem to try with some kind of, maybe some reinforcement learning algorithm, try to set up kind of environment where you delete edges, and rewards will be based on, you want to check that the resulting graph is connected, what the diameter is, and so on. So it would be a fun thing to get started with. You only need standard graph algorithms to set up the reward function. So it's probably something that's easy to get started with. I have no idea whether we can actually improve it or not, but it could be a fun thing to try. And a third problem is a similar problem to what was suggested on Zulip, but maybe an easier version of that. And it's a very classical puzzle. How many points can you have on the n by n grid without having 3 points on a line? Here again, there's an easy upper bound. You cannot have more than 2 times n, because every horizontal line contains at least 2 points. Question is, can you actually do 2 times n? Turns out you can, up to some large value of n, but the results start breaking down in n equals 50-ish range. It could be interesting to see if machine learning methods can do better than standard methods on this problem. This is a very, very classical problem in combinatorics. Doesn't have any deep implications. Again, this is just a simple, more like a puzzle, but it would be interesting to see if we can do better than standard methods.
What is the construction that rules out the if numbers up to 50?
Yeah, for some reason, it's easier to find constructions for some even numbers than some odd numbers. For some symmetry reasons, I think. Best constructions are always some symmetric things, and it just works out better for even numbers. I remember reading that it's.
But then the argument breaks down at 54.
Yeah, so they couldn't find constructions for 54. So you have to find constructions, and it's a little bit easier for evens, but it's still not that much easier, I suppose.
So people just found there's no argument for why.
Yeah, you just find constructions. So these are the 3 problems I wanted to get started with, but I would be very, very happy if you guys can also suggest your own problems. So what I would love to do now is just pass it on to you guys. If anyone has nice problems, please, brave enough to present, please do so. Excellent. You want to present or just on the blackboard?
Oh, I don't have it.
Okay. Just stop presenting them.
In principle, we have microphones, so but go ahead.
Yeah, I'm thinking about this fever mutations. Fever is a directed graph, and you have the directed arrows, and this is actually a multi-graph. We may allow as many edges as we want, and then quiver. So this is a quiver. Then mutation of a quiver can be defined in 2 steps, but I will not do that now. I'm just proposing a question. Or can I do that now? I can do that later. Quiver mutation arises from the study of cluster algebras, and also it is related to Seiberg duality in string theory. So, yeah. And then here we don't have a cycle. Do we have a oriented cycle? We don't have an oriented cycle, do we? No. So if we have a quiver and then you mutate this quiver many, many times, sometimes, if we start with a quiver with an oriented cycle,
go ahead. I'm just trying to get the other camera controls out.
This quiver has a cycle, oriented cycle here. Then you mutate this, and then you have, mutation can go forever. Sometimes it ends in finite number of quivers, and then you don't get any more new quivers. But sometimes, anyway, so there are many different classes. The question is, sometimes if you have this kind of quiver, the oriented cycle, and you mutate, then you may end up getting with something like this. So there's no oriented cycle anymore. Then this quiver is mutation equivalent to this acyclic quiver. Acyclic means there is no oriented cycle. But other times, you'll never be able to get an acyclic quiver in mutations. But if a quiver is acyclic, then it is fundamentally different from a quiver with a non-mutation acyclic quiver. Does it make sense? So if you cannot get rid of this kind of oriented cycle in any ways, in mutations, then such a quiver is a kind of infinite object. If you can make it equivalent to an acyclic quiver, then it is kind of a finite object, kind of. So we want to know if there is a given quiver, maybe we want to know if it is equivalent to an mutation equivalent to an acyclic quiver or not. Sometimes you will never be able to get this kind of quiver in mutations. And moreover, there may be many cycles. So let me create one more cycle like this. Then, so even if we cannot make it mutation acyclic, but can we reduce the number of cycles as much as we can, as small as possible? And then this can be an invariant of a quiver, so the smallest number of cycles in the mutation class. But can we determine that number? But that's the question. I think no algorithm is known, of course, algorithm can be, no, there is no algorithm, and I believe this is NP-hard problem. But can we use the reinforcement learning, for example, to reduce number of cycles as much as we can? Then in certain amount of mutations, we determine if the quiver is a mutation equivalent to an acyclic quiver or not. If it is not, then what's the smallest possible number?
Why don't you define the mutation now?
Okay, the mutation. The rule is, let's say this is now let me. Okay, so now the vertices have names 1, 2, 3. The mutation, let's make it this mutation at vertex 2 is first find out all the paths oriented like a path which goes through not paths but like 2 arrows like this, which goes through this vertex 2. Okay, and then whenever you see such 2 arrows, consecutive 2 arrows, you then it starts from 1 to 3, right? 1, 3, and it ends at 3. Then you add 1 arrow. So in this case, you have to arrow. If we mutate this quiver, the first thing is you add this arrow. Okay. So then we have oriented 2 cycle. Then we just cancel them out. So this direction, 1 cycle, 1 arrow, and this direction, this arrow, then they cancel each other. That's the first step. First step with this step. And second step, after you do this for all the possible pairs of or 2 arrows of 2 arrows passing through this vertex 2, and then get rid of all 2 cycles. And then step 2, you reverse the directions of arrows that touches this vertex 2. Okay, then so then that's it. Step 1 and step 2. The mutation of this quiver at vertex 2 is this. Okay, so now you can see that this had a cycle, but now it doesn't have a cycle. So this is mutation equivalent to an acyclic quiver. Okay, any question?
So can you describe this in terms of the adjacency matrix?
Oh yes, the agency. Yeah, that's right. Yeah, there is a very simple formula. I can probably show you the formula. I mean, if I have a laptop, but I don't. Yeah, it's basically like a tropical thing. It is related to tropical, arithmetic, tropical geometry even. Anyway, so yeah, there is. So it can be easily computed using some matrices, and it basically comes down to matrix multiplications.
Okay, so that's good. With this definition, is mutation an involution if you do it twice?
Yeah. It's involution.
Okay.
But if I mutate this, maybe I didn't understand mutation correctly. But if I mutate this again, I don't go back to you.
Okay, let's do that. Step 1.
I invert first, and then I.
First you arrows and then you.
So mutation at 2, and then if you do it mutation at 2 again, then you go back.
First you add the arrow.
First I reverse the arrow, because otherwise I would be going from 3 to 1 now. So
yeah, that's it.
Yeah, okay, good. Yeah, suppose more cooperation. Okay, thank you.
Okay. So the reverse step of mutation is all arrows, or just the ones connected to 2?
Ones that touching this number, the vertex.
Okay.
Right, instant.
So why don't I end up with why do I end up with the same thing? And I end up with an arrow with 1 to 3.
Yeah, but because you invert.
3 to 1.
So at the moment you go from 3 to 1, and then after that you invert the arrows.
Yeah.
Oh, I see. Yeah. Okay. So that was like
So this is the simplest possible example, except the rank 2 case. If we have like a 10 vertices, it will be very difficult.
Like the original Cyborg duality.
Yeah, Cyborg duality. Then if you just Google cluster algebras, then you find out.
Can you remind me what acyclicity means in the class?
there. I mean, there's this more complicated. Well, there's this more complicated thing which has flavors of relation. So you have to have a super potential. So
it's not simply combinatorics.
But it's related to this. It's like a simplified but closely related thing.
Yeah, if there's a cycle, then we can define superpotential Jacobian algebra.
The deleting of the arrows is some integrating out of massive nodes or something like that. And so the number of cycles of the minimal thing is some minimal amount of superpotential you have. Or something like that.
But I don't think there is any algorithm to compute that minimal number of cycles. But if we go to some direction of mutations, then we may increase the number of cycles. If we choose a clever direction, then we may decrease the number of cycles. It's very difficult in general. Can you do that using reinforcement learning?
There's a lot of ways that get related to geometry. No immediate relation. I believe you, that's a hard problem.
Yeah, it is a hard problem, but can we use machine learning?
That's analogous in spirit to some of the not dirty problems.
Yeah.
As I said, it's NP hard. So the question is again, how hard is it on average?
How hard
is it on average?
Average, yeah, I don't.
Are things known in special cases?
Oh yeah, thinking quivers, and then quivers coming from the surfaces, and there are some special cases. Then for those cases, we have classifications.
Okay.
So in general, this is difficult. I mean, this is the simplest possible cases. If I put 10 vertices and put as many arrows, an arbitrary number of arrows. Okay, that's a good question. Yeah, let me think about this.
Is there a family that's known how to some sort of adversarial attack on this, where it's known that you can't?
Yeah. So we know the class of mutation.
So let's say I want to construct something that can be brought to acyclic, but it takes the maximum number of mutations.
Yeah, I think there are some families. Yeah. So I don't have all the information up in my mind, but there are some very well-known cases. For example, the E8 quiver. Probably may start with the E8 quiver and then mutate this 100 times or 1,000 times in arbitrary way. Then there will see a lot of cycles. Now, can we go back to this acyclic situation? That may be the very basic practice. Exercise. And then if it works, then we may consider more complicated.
Do you ever consider setups where so your labels 1, 2, 3 are just labels that you gave it that are arbitrary? Do you ever have extra integers on the nodes and constraints on those integers relative to the edges?
This should be like skew symmetric. I mean, if you consider the
He's saying, suppose you add extra numerical indices to this.
Exactly. That carry meaning and aren't just labels.
Yeah, just labels. Yeah, 1, 2, 3. Yeah, we can. Yeah.
There is an interpretation where
So decorated graph, right? Another integer and.
Do you have some sort of constraint that the number of arrows into a node is equal to the number of arrows out or something like that?
No constraints.
There's something in physics called anomaly cancellation that requires something like that, and it's a set of extra constraints that would be a special subclass of things.
I see. But we may put any conditions we want as a starting point. We may, If we consider arbitrary number of arrows, then there will be too difficult at first. So we can start with two. So at most 2 arrows at the beginning. Then we can see what happens.
Before the cluster algebra just came out of this representation theory,
fever itself has a long history. Yeah. It came from Gabriel's theorem, at least the 1960s. But mutation of fevers were introduced by Fomin and Selevinsky, and then also in physics, Seibert introduced the mutations.
It was even before that, it was algebraic valence. But anyway, I don't follow a lot of the physics, but there's this very rough picture, which was in this old literature that was like the Denkin diagrams, which if you're familiar with physics, there's the finite dimensional algebras, and there's the affine ones, and there's the hyperbolic ones. And it's kind of like that. And from that point of view, the finite ones, you can completely understand and get some kind of a finite graph of everything you can get from the convention. The affine one, you can also completely understand, but they also take that hyperbolic one, that's just some sort of very complicated tree structural graph. So that's the kind of naive picture of it. So
right.
That's kind of why I'm asking for some more specific conjecture or something that we can look at.
Okay, let me think about it. Yeah. So finite types and affine types, we know, but the hyperbolic types, probably there should be some conjectures.
But what we say about them.
Okay, let me think about it. But without those conjectures, still, I believe this makes like a problem in search of that.
Yeah, thanks. Lots of problems, right, that we're talking about. I mean, made progress on your sleeves.
Yeah, we can talk about that as well. Does anyone have any other problems that this happens? We could have like even more problems.
Your third problem sounded like shouldn't be very manageable to research.
Make more? Yeah, so it's very similar to the isosceles triangle. So I'm optimistic that's something like that can be very good. Like the make more method already worked on the similar problem, so it should work here as well. So that's why I think I'll be the problem. Any other problems that we should talk about? Yeah. Okay, so I'm just going to get back to the last problem that I just talked about, the no tree line. And maybe one reason why I do think that's a good problem is because we have methods that already worked very well for similar problems. So if instead of forbidding 3 points in a line, you forbid 3 points that form an isosceles triangle, so you have the n by n grid, and you're not allowed, you want to choose as many points as possible without having 3 points that form a triangle with 2 sides equal. Very similar problem. And for this problem, our machine learning methods have worked amazingly well. So we managed to find constructions that outperform set solvers, other methods, by just doing some very simple tricks. So this, I can show you more constructions that we found and so on, but this is basically the motivation why I put that problem on the list.
So why don't you describe your method?
Yeah, okay. Okay, so the method that we used is something we've been working on with Jordi Williamson, Francois Chaton, who is here in the audience, and Jordan Ellenberg. And the idea is very simple. You have some kind of problem, and you have some kind of search algorithm that works pretty well on the problem already, so it produces some good constructions. But you want to somehow boost those constructions, make them even better. So what you do is you first do your standard methods and produce as many good constructions as you can. So you create a database of lots and lots and lots of pretty good constructions. So you want to make this database as good as possible, with as good constructions as possible. And once you have enough good constructions, there's going to be something in common with them. So imagine you have a problem where you can see that there's some kind of pattern going on, but you don't know what this pattern is. What you can do is create this huge database of lots and lots of good constructions, and then use some kind of machine learning to try to find what this pattern is. So that's what we did. So step 2, once you have a big database of lots and lots of good constructions, let's say with lots of points in them without tree and line, you train a model on it, let's say a transformer. You tell the transformer, please figure out what's in common globally in all of these constructions that are in the dataset.
It's a generative model that generates
exactly
solutions. So it's something, there's some probability distribution of the solutions, and you train it on the solution.
Exactly.
Step 1.
Exactly. So you want to train some kind of generative model, because the idea is after you've trained it, you ask it to generate you more constructions like the ones in the database. So you train a model that understands something about what's globally in common between all these constructions, and then you ask it to give you more constructions that are like these good constructions in the data set. So that's step 3. Generate new constructions from the transformer. So that's the bare bones of the method.
There's a step of local optimization.
There is, absolutely.
It's essential.
It is. That's going to be step 4. So that's the main idea of the method, that if you have a big enough database, then there's lots of patterns in them, and the transformer will figure out what's globally in common between all of these good constructions. It will understand it, and it will be able to generate you new constructions that fit into this database at a much faster rate than you can find them with standard methods after some kind of threshold is passed. That's the idea. In practice, you need one more step. Once you generate new constructions with a transformer, it will make some small local mistakes, so it will get globally the structure right, but it will.
It's just not in practice, it's a principle, because your steps didn't say anything about what you're trying to optimize.
Yeah, but that shouldn't be any.
No, that's essential. How can the system find good solutions if you haven't told it what to optimize?
But you showed him many, many good constructions.
Yeah, let's say you got things like that, but it doesn't know what it's trying to optimize.
It could be that by chance it produces some of them that are better, but local search is essential. I agree.
Well, so the minimal step 4 would be to pick out the top guys by that criteria.
Yeah, absolutely.
Good step somehow include this one.
Absolutely. You need something.
Yeah.
I agree with that. What you suggested is the absolutely. But it's even better if you just put some kind of local search. It's on these. So this is just a very general algorithm, but it works really, really well on similar problems. And
well, pick up step 5 is pick out the top ones.
Yeah.
So this is, I mean, the words that, I don't know if you said, but combinatoric optimization. So we have some kind of big configuration space, which is maybe lots of given choices. We have some conditions which you could phrase in terms of which condition just depends on new choices. And then we have some number or something that we're trying to maximize. And so that's kind of the class of problems, which you're isosceles.
Yeah.
So step 5 is pick out the top.
Pick out top ones, this new database.
Yeah.
Exactly. So that's a kind of a spin on standard reinforcement learning methods, and it seems to work really well on many kinds of problems. So for example, in the isosceles problem, where you want to have as many points as possible without any isosceles triangles, we created a big database of lots and lots of constructions with hundreds of points. We trained a transformer on them, and once we did this loop, we ended up with lots and lots of even better constructions. We iterate and constructions get better and better. So in some sense, this is just an easy way to take any standard optimization method, put ML on top of it, and get something even better. And many times it works, many times it doesn't. Most of the time it doesn't, but for these kinds of problems, I am pretty optimistic. So that's why I suggested the third problem with the non-tree methods.
So I have a nice, this is a lot like a genetic algorithm where you take pairs or solutions or pairs of programs and solutions and combine them in some way to get the new ones. But here, we're replacing that genetic combination set with training the model, the transformer, and then generating things like that. So we refer to it as a population genetic algorithm. This population is all kind of combining it.
That's very well when you have a problem where there's some kind of structure and it's really hard for us to really understand what's going on. But these models can still pick up something about the structure. And it will take me a few minutes, but I think I can pull up some pictures that we found.
Do you have a sense of why local search sort of works here? Sometimes,
yeah,
combinatoric problems I'm used to, you sort of have some approximate algorithm that might get you somewhere nearby, but you're not guaranteed that there's a solution close. Thinking of like continuum problems in string theory, and then if you bump to the integers, you just.
That's why you need step three.
Yeah. Yeah, I guess that's what I'm asking. Is there a sense of why is there an understanding of why the generator gets you close to a good solution? Yeah, I guess it learns it.
But just random. Well, yeah, why are solutions like each other?
You definitely want your score function to be nice and continuous, and for some problems this doesn't work.
What's an example? I guess it's lots of examples of problems where it doesn't work. That would be like a very broad question we can ask: why does some method work? What problems does this method work? What problems does this method not work?
I mean, if you understand some of the biases for the optimization algorithm and the architecture, even if you're not able to solve it, it can tell you something. I mean, to your point, tell you something about the kinds of solutions and the underlying structure of the problem.
I mean, this main choice is representation you use for this model. Step two, everything else is kind of determined, but they feed in with solutions. Representation. You're different.
So I missed the end of step three, but what it gives you in the end is examples.
Yeah, okay. Exactly.
Do you have a sense of like how you would take, I mean, in some cases, maybe looking at those examples, that's enough. You find a counter example, or you're able to say something about a bound. Have you thought about like how you might, the process by which you might analyze those? I mean, you could imagine coming up with an example that like, it works, but you don't really know, it doesn't tell you something broader. Do you have a process for how you might?
Ideally, you find better constructions and you will get some insight out of it.
Yeah.
Sometimes you try and you don't.
Yeah.
There's this fun search. It's a lot like this, but instead of the transformer for the step two, the thing, it's a different language model, and it generates a program that tries to generate a solution. And then that goes aggregated into, then you can look at the program.
Right.
So my story of why this method works for this problem is because there's very clearly some kind of pattern going on. So if you look at the best constructions, so this is the isosceles problem. You have to choose as many points as possible without 3 points that form an isosceles triangle. If you solve it for small values by hand, these are the best constructions. So we can check that you don't have any 3 points that form any isosceles triangles here. And if you go higher and higher, you will see that there is clearly some kind of pattern happening. Oops. But it's very hard to tell what exactly this pattern is. So that's why it seemed like some kind of machine learning method would be a good thing to do here.
And these examples are unique for each n?
No. So for example, for 27, there's a construction on the left. It looks kind of like a bear, maybe, but there's also this butterfly. So these are very, very different.
So there are several, like hundreds?
For some values, and it's unique. For some values, there is many optimals.
Just to be explicit, the way you feed it into the transformer is the principle of it looks at zeros and ones, but then you tokenize that.
Exactly. Exactly. In practice, you don't want to feed in a 48 times 48 long vector or 27 times 28, 7 or something. It's just a bit too long. That's making it running very slow. So in practice, you want to tokenize.
You don't tell it the 2D structure of the
We didn't.
you consider trying to tell it the 2D structure in some way. That would seem like it might be advantageous.
We didn't so much care about this specific problem. We cared more about whether the method
It's not
works.
that hard to be.
We didn't try that, but yeah. Also, symmetry could be encoded. It seems like the best constructions are symmetric, so that's something you could easily.
Did you get ones that were not symmetric or all of the?
Yeah, so actually, so we tried for 64 with standard methods. This was the best we could get. But then we did this method, then it actually ended up finding something that wasn't completely symmetric. It's almost symmetric, and maybe it's actually symmetric vertically. I'm not completely sure. No, it's not, because there's a point here and not a point here, and not a point here. Maybe it's, oh, but maybe it's like symmetric like this.
No,
and
it's not.
I'm not actually. Oh, it's not.
On the top right, there's a point.
Yeah.
It's on the.
Yeah, well, it's very close to symmetric anyway.
And the local search is like a greedy thing where you just
So
see if you can have
this we found with like every single trick that we could throw at it. So
what local search did you actually do?
So this we did by throwing every single insight and every knowledge we had about the problem. But when we improved it, the local search we used is actually the most trivial thing. You have given a point set, you delete points until you get rid of all isosceles triangles, and then you add points randomly for as long as you can. Simplest possible local search, and we still managed to beat the sophisticated handcrafted
And you choose the ones to delete random.
Greedily, I think, delete the ones that are the most.
Greedy is different from random. You take the first one, so you take the other points some random way.
Greedy in the sense that you delete.
If it can't be taken out, you take it out.
Okay, then the algorithm was delete the point that is in the most isosceles triangles and repeat. In greedy in that sense, I guess. So this what we notice is the higher n we go, the better this method works. So for 100 by 100, this is the best we could find with standard methods, 154. But actually, by doing that method with a very simple local search, we boosted that to 160. So I feel like this can be dropped onto any kind of standard method and just boost the score a little bit. Sometimes it works, sometimes it doesn't. Most of the time it doesn't, but for problems like this where there seems to be some kind of pattern going on.
Use some measure of the error, so as a function of the size of the grid, the distance, like how much local search has to be used relative to as a function of that. Between the transformer generated samples and the things that the
yeah, so there's definitely a balance there, and I don't really know this balance. So you want your database to be big enough, otherwise you won't be getting any learning. You want your database to consist of good enough constructions, otherwise you won't find any patterns really. But you don't want to spend 5 months doing local search either, so there's definitely some kind of balance. It's just very dirty. You just have to experiment with things and see what works well.
Another kind of experimentation to this question of whether it's a problem, simple variations on this problem.
You're saying how can we tell?
Yeah, tell you something about this problem. It has structure. Almost fine, it's good at. Some problem that seems very similar to us, but in fact, because it can't find that structure.
Yeah, so for the node 3 and 9 problem, I tried for a few hours, and I did manage to find the best constructions up to n equals 35-ish, which is not quite 50 yet, but with just some very straight up reinforcement learning, it did seem to work, but that's just based on a couple of hours of just trying things.
Well, that actually raises another question. Is there any kind of systematic way of saying how much effort you put into the problem? Of course, it's hard when you're doing lots of experiments and not even anything we would say. I ran for this amount of time compared to the problem. I ran for that amount of time. Just a systematized discussion. So maybe a number of iterations. It's not something that some further statistic you can.
I think the hard thing is even in more mainstream machine learning, right? Like you never know if a method didn't work because you just had the wrong hyperparameter. You should have used a slightly different representation. The scary thing. Yeah. Right. Or the scale's not big enough to see advantages.
Yeah, but it's still to keep more data to ask these questions. How would you, your original, your first problem, on the face of it, it's one of it in terms of real numbers.
How would be? I would just treat real numbers. I would just disregard the problem probably. So for the first problem, so my question was, how do you approach the problem with the chessboard? The lines have a slope that's a real number and the y-intercept that's a real number as well. My first thing I would try is probably just quantize the problem, discretize the problem. So instead of working with real numbers, just work with increments of 0.1. See if that works. Maybe there's a smarter thing to do. I don't know. I don't suspect that this problem is easy. They did try find n-2, but they didn't try any sophisticated methods, especially not sophisticated computer methods. So could be that n-2 construction is just something complicated, but it would be really interesting.
Your problem actually reminded me of a different problem in physics, which I could pose, but I didn't prepare it, so probably I'm not.
Yeah, please go ahead.
Do a good job. But I'll try to write something down, but I can't remember. So yeah, as I said, I didn't prepare this, so this will not. I can't remember all the details. The paper is maybe 7 years old, and I won't be able to remember it. But so what people did, and there's something in physics that's called a tadpole conjecture. And what it is it's essentially a conjecture of how you can distribute integers in a lattice with a certain inner product such that the number with respect to this inner product is small and some other condition is still satisfied. So people looked at something at a space, complex four-dimensional space, the Talia fourfold, which is the product of two Talia two-folds, but there's not, that's not very important for the set of the points. You have a lattice here of signature 319. You have another lattice here of signature 319. And now the name of the game is to choose integers within this lattice, such that I think the number of, so let me call it integers that go with the positive eigenvalues, AI, and the one that go with negative BI, and the same here. Now you want to choose these integers AI and BI such that with respect to the inner product, I think it's the product between the A's and B's is 0 or non-zero. Can you remember?
Sorry, what's the question?
So for moduli stabilization, the product between the AIs and BIs has be either 0 or non-zero.
I don't know.
Okay, so it has be either 0 or non-zero, and you want this with the least amounts of AI and BI. So this looks like a problem where you can sort of, people try this with different random evolution algorithms, and there are sort of problems now where this product sort of gets very close to a target number, but then they couldn't quite hit the target number. Sounds like you can create this database easily. Just by drawing random numbers, if you choose enough integers, you get to some number, and then you can try to make this better and better. And there's a specific goal you would like to hit here, which would tell you something physically very, very meaningful. To tell you whether you can essentially. So if you use string theory as a model for the real world, this would tell you whether you can get something that's on string theory that's consistent with cosmology.
So, and the conjecture's going to be false. It's more complicated.
The conjecture is known to be false for small. I mean, for small
But not for K3 times K3.
For this one, it's unknown to be false.
Right, and so doing this for this case, even in a simple case, could disprove the conjecture, even in this very vanilla case.
Yes. And the conjecture seems to be true for large enough middle cohomology dimension. It's known to be false for small cohomology dimension. For this particular case, it's not known. But it's a very simple case. It's really, you just have a lattice. I mean, you have the intersection lattice on the middle cohomology, and then you just need to find these integers such that such that with respect to some inner product, and they are zero, not zero, and such that the total number of integers sums up to a number that's small enough.
That's probably worth maybe look up the details.
Yeah, I can do that. Yeah. But yeah, so it's similar in flavor. You just the numbers. Of course, if I pick all of them, so probably it has to be non-zero. So if I just sort of pick something everywhere here, then obviously I satisfy all the constraints, but then I much be above the number, the target number, to get below some target number.
Is there some way of making this like classic response? I mean, so for some of these other flux problems, although they sounded, 2D flux back here, sounded the first of the one, they were turned out to be this very so maybe that's the case for this one.
Yeah, as I said, I hadn't thought about it at all, but it's so you need to find points on the lattice that satisfy certain constraints, and then there are ways of getting sort of close to the optimal solution, and then maybe make more in the locus search.
Yeah, and one thing in this part natural is this self-dual lattice, and then self-dual lattice.
Yeah.
It's much more natural problem.
Yeah, so this 319, what is this? This is the root lattice of E8 plus E8 plus something that's called so something with hyperbolic signature. You might see. That's a lattice you have. And then you choose the basis in the middle cohomology of this thing, and then what then has to be G4, which G4 has to be less than or equal to some number, where G4 is essentially just the sum of these AI DI or AI DI, where DI is sort of the basis for the middle cohomology of this four-pole, and you just have you have the sum batch product and you integrate it. And this has to be less than or equal to some number. Yeah, I'll write something on Zulip. Yeah.
In the spirit of just testing the method and understanding them better, we go back to like the sphere packing. Can you find sphere packing something? Are sort of high dimension versions of people talking about so we're trying to switch over to this foundation.
Foundation.
Okay, you want to present that? I really don't.
So do you have a vague idea of having some kind of bigger projects? So this week we'll have 2 talks about some databases authored by Henry. Yeah. So on Wednesday, tell us about your database, which is more algebraic combinatorics. Tomorrow we will have a talk by Jan Hutber. I don't know how to pronounce his name. I've been practicing, but I still don't know. So his Dutch names are hard. And so he will talk about different kind of database, what are databases, different graphs and graph properties. And it would be nice to have some bigger project or get started on some bigger project where we train some model on this big database of graphs to be able to predict various parameters from other parameters or from the graphs themselves. And this is some kind of really general foundational model.
So the databases have big list of variants.
Yeah, definitely. Tomorrow's one definitely does. I don't know about this.
No, but I have some ideas for things that one could do.
Okay. So can you maybe tell us a small preview to your...
Yeah. So we've been working on putting together a database of different problems related to things in algebraic combinatorics with the goal. So our goal was less about putting together a big set of things that one could train one model on, and rather looking at like, okay, ML for math seems like a promising area, but most math problems, research level math problems have a high knowledge barrier. And if you go and look for papers where people actually put together these data sets, they're often impenetrable to the non-experts. So our goal was to collect a bunch of problems that represent either foundational results in algebraic combinatorics or open problems, put them in context so that someone, say, from computer science who was interested in ML for math but was not an expert in any math field could understand what the problem is, why it's important, why people care about it, structure it in a way that it's like amendable to machine learning out of the box, and then get these all together in one place where people can easily access them. So a little bit less on like, I don't know how you train a model on all of these, and more about like trying to introduce AI to math to the broader machine learning community.
Okay. So that's great. So we have two very, very different data sets. I mean, we can go in all sorts of directions with this big project. I don't think...
But the basic idea is that if you have not just a lot of graphs, but a lot of variants, one model that predicts many of them could be predicting.
Exactly. So tomorrow's data set is exactly like this. So lots of graphs, 100 columns with different parameters.
So once one had the foundation, some other applications.
I think that would be a big project, and no hope that we can do it this big, but it'd be nice to get started with something like this. Yeah, some sense of that.
Yeah. Is there a possibility of a compute resource for that? Whenever I hear foundation model, we're going to train a foundation model. The question is always, do we have the compute to do it?
What it is, I mean,
yeah.
It's not necessary. Sorry, can you hear me?
Yes, we can.
Yeah, it's not necessarily as big as language model, because the thing is that when you have a large language model, they need a lot of compute and because they have a lot of tokens, and they have a lot of tokens because they want to train it on the scraped internet. So they're talking trillion tokens. In our case, probably a very large data set would be probably in the hundreds of million, probably, or several billion ranges. So the amount of compute that is needed is not as important as what we think when we think of language. Supposing that we're doing, foundational model for formalized mathematics. That is, the graphs are already represented as sequence of tokens that represent a graph. It's not a graph in natural language. I don't even know how we do that.
Well, I guess another preliminary question is that there are several machines that represent a graph. You have to choose a primary representation. So how do we make that choice?
Yeah, there's Brendan McKay at Australia. He has this graph 6 Gen GP notation, where he uses to generate all small graphs, and he does this isomorphism checking very easily.
Okay, well, that's interesting. I mean, but what there's just other graph representations too. So what criteria and how do we decide which ones to start with?
It's a very compressed representation.
Very compressed. So
that might be good for storing, but it's not obviously what you want to train.
Yes, that's what I would be worried as well.
Yeah, I think he uses the upper triangular adjacency matrix and he like parses the matrix into like bit sequences and changes it to ASCII because he wants to compress as much as possible.
Okay, that's not too bad. So you can decode it locally. So
yeah,
you can just start decoding in the middle.
Yeah, if you know which part that.
Well, the question I would ask is, suppose so there's a representation, and I could vary it and take different representation. So, what tests will we make to start out next to that? The whole model, right? But maybe we'll just start on a subset of the data and make some other tests.
Absolutely. So we should start with lots of small graphs and like 2 parameters. And
maybe what looks so small graph with small graphs is not good for big graphs.
That's true.
So it's a test of their thought.
Yeah, or outlining some small experiments to just start.
Yeah, what's a good experiment to like this one?
Yeah, I think it all comes down to interest. Like, are we interested in trying this big foundation? Are we more interested in trying some smaller problems this week? I think it's really up to you guys. You guys start more invested in. So.
You could put a bit into it.
You guys know which problems you're interested in, or what's
all of them?
All of them. Okay.
So there was this approach that Drew in number theory were talking about. Let's actually form working groups and divide up problems among the working groups. So that's the advantage that people focused and work together.
Yeah. So should we write up the problems on the board and
yeah,
okay. I can try to do that. Okay. So what problems should we have here today? We have figures. What else did we have?
Chessboard.
Chessboard. In the line. I will group it together with isosceles problem. They're very, very similar. So various combinatorial problems on the n-by-n grid. Yeah, oh, very good. Thank you. What else was there?
Spanning tree in the cube.
And there's cubes. Anything else that I forgot?
Foundation model is separate.
Yeah, I think so. I don't want to put. Okay, so let's just go by show of hands. Who would be interested in working on rivers? Okay. Should I put number or just you can?
Yeah, you put the number.
Okay, so make sure you know each other. And, who's interested in the chessboard? Okay, have fun.
There was also one interested in rivers.
Oh, I'm sorry. Okay, fine, very good. I'm sorry, I didn't catch it.
Calls me too.
6. So 6 verse. I'm very happy to work on any of the problems, so I don't think I'm going to go to chessboard. I'm particularly interested in Cypress 2. I think that would be a fun problem to do. Various problems on the n-by-n grids, streamline, isosceles 2. Myself as well. I like this problem.
Someone in Zoom.
Someone in Zoom. Oh. Okay. Thank you. I'm always forgetting to check students. Okay. That problem. Okay, that's lots of people as well. I counted 4, 5, some half, and anything on Zoom. That's fine for tadpole. And anyone for the Irish cube, I'm spanning subgraph of the cube, two edges. Okay, so that dies.
Yeah. Why don't we pick one person from each project to start a topic and start coordinating with others.
Topic on Zulu.
Yeah, absolutely. Yeah. So
Yes, I can do it.
Then we can join as desired.
Who wants
to be school name?
So chessboard, we can just talk and see if we can do something. 3 and 9, SSS problem. We already posted that SSS problem, so I don't think we need to post it again. There's already a discussion, there's a separate section for it. Can you guys remind me who was interested in the 3 and 9? Okay, awesome, all right. And someone on Zoom as well. Who can write about the tadpole problem? So that, okay.
Perfect. So we'll have some discuss.
Yeah.
Of course, people can meet informally and discuss these things. So that's yeah, very good. Other topics? So you already scheduled some talks for
tomorrow on Wednesday morning.
Thursday after to have another talk at 1:30, a discussion at 1:30 about the Mistral AI models and what we might try to do with those. When can we do the talk about the foundation?
The first day is Monday, Friday.
Yeah, I mean, well, I mean, maybe Friday is good. Okay.
Just a question, because I asked it. Why Mistral versus like Llama? Is there something that they're doing?
Yeah, they're offering the users credit.
Oh, yeah. That's a very good reason. Yeah, I forgot. You mentioned that last week. Thank you. Okay.